Okay, in this tutorial we're going to talk about the normal probability distribution. We've already talked about discrete distributions. Now I'm going to talk about the first continuous distribution that we'll see in this course, which is the normal. So if you think about discrete distributions, you often have several distinct possibilities. Think about it in terms of number of students that show up for class. It could be 2, 4, 6, 15. Whatever the possibilities, but I can count the number. There aren't an infinite number of possibilities, and each one has its own probability, right? So it may look something like this. In a continuous distribution, there aren't just, say, 4 or 10 or 400 distinct or discrete possibilities. There's an infinite number of possibilities. It could be 2.1, and it has its own probability. It could be 4.065, and it has its own probability. Think about it in terms of, let's say, pounds of coffee harvested, right? There's really no limit to how many possibilities you could have. So you end up having a lot of little probability bars here, right? And in fact, if you take this to the limit and there are an infinite number of them, instead of drawing individual bars, you can actually draw a curve. That's what a continuous distribution is. And the normal is a specific type of continuous distribution. A few properties of the normal that we need to be aware of. It is continuous, right? So it doesn't have a distinct or discrete number of possible outcomes. Secondly, it's bell-shaped. You might have heard the normal curve referred to as the bell curve before. The bell curve is the normal curve. Secondly, it's symmetrical, right? So in other words, if you take the midpoint of the normal curve and fold it over on itself, it would perfectly match up. The two halves would perfectly match up with each other, right? It looks exactly the same to the left of the center point as it does to the right of the center point. And it's completely defined by its mean and its standard deviation, right? So the center point of the normal curve is the mean, or in other words, the average of the normal curve. It's also the median of the normal curve, or in other words, the point at which 50% of the probability is above the median, 50% of the probability is below the median. Now the standard deviation is a measure of the dispersion of the points around the mean. Right, so standard deviation very small, that means most of the points are clustered very close around the mean. So for example, if I took this normal curve and I kept the mean the same, but I lowered the standard deviation, it would just kind of look skinnier around this point. On the other hand, if I increase the standard deviation, there would be much more dispersion around the mean. So it would be much flatter like that. All right, so we're just going to talk about some foundational components of the normal curve. It comes up a lot in a lot of business contexts, so it's important to be comfortable with it. Okay, let me draw another normal curve here. When you have a probability function like the normal curve and you draw it like this, you can think about the area under the normal curve as the probabilities, right? So if this is the mean, let's say that this is a normal curve with mean 5, right? So that actually means that if I do a random draw from this normal curve, then the probability that I get a number greater than 5 is 50%, and the probability that I get a number less than 5 is 50%. So probability greater than 5, that actually means that literally this area over here, the area to the right of 5, that area is 50%. In this area, over to the left of 5, that area is also 50%. So that's important to remember. We can think about the areas under the curve of under the normal curve as actual probabilities. That's exactly what they are. All right, so I say on this particular normal curve, let's say I have a point. So if this is 5, let's say 8 is somewhere out here. All right, so I want to know what's the probability. I'm going to do a random draw from this normal distribution. What's the probability I get a number greater than 8? That probability is exactly this area. So if I can figure out this area under the curve, then that is the probability that I get a draw from this distribution that's greater than 8. All right, so let's say that it's always useful, whenever you're doing problems involving the normal curve, always begin by drawing this. So let's say, and we'll talk about how to calculate these in Microsoft Excel in a moment. So let's say I tell you, you have a normal curve with a mean 5. All right, so I'm going to use this Greek letter mu for mean. That's commonly used to denote mean, and standard deviation of 2. So standard deviation, again, just means how much the points are dispersed around the mean. I'll mention that more in a second. And then I'll say, I'm going to do a random draw from this particular normal curve, what's the probability that the number I get is greater than 8? And you plug that into Excel and you get an answer of 72%. That can't be right, right? If you look at this, if you draw it, this is the probability you're looking for. You know it's less than 0.5, right? This entire probability to the right of 5 is 0.5, so you're taking a slice of that. So if you got 72% from Excel, you must be doing something backwards, you must have made an input error. So just by drawing this, I know that the probability of getting a number greater than 8 is absolutely less than 0.5. Okay. Some properties of the normal that are very nice to know. There's some very handy things about the normal curve if you know the mean and standard deviation. All right, so this talks a little bit more about specifically how do I interpret the standard deviation? What does it mean? So let's do a curve with mean of, let's call it 20, standard deviation of 3. Okay, so that's sigma. This Greek sigma denotes standard deviation. So the mean's 20. Now I can go one standard deviation out here. This is 23. Then I'll go 2 standard deviations, 26. Then I'll go 3 standard deviations, 29. I'm just denoting the standard deviations on my curve. Now let me go the other way. One standard deviation below is 17. Another standard deviation below is 14. Another standard deviation below is 11. So why are these standard deviations important? Because I know the area of the curve between these standard deviations. So this is mu. This is mu plus 1 sigma. This is mu plus 2 standard deviations. This is mu plus 3 standard deviations. And this is the same over here. Mu minus 1 standard deviation, mu minus 2 standard deviations, mu minus 3 standard deviations. All right, so I know I have some rules of thumb here that I can use. If I'm going to make a random draw from this normal curve with mean 20, standard deviation 3, I know that the draw is going to be somewhere between 17 and 23. Or in other words, somewhere between 1 standard deviation below and 1 standard deviation above. It's going to be in this range about 68% of the time. Right? So 68% of the time I'm going to be in this range. So for example, if you have an investment and the average return, the returns on that investment are normally distributed, and the average is 20% and the standard deviation is 3%, then I know that there's a 68 probability that the return is going to be somewhere between 17% and 23%. I can keep going out 2 standard deviations. So now I go, so this 68% is from here to here, minus 1 to plus 1. What if I go from 2 standard deviations below to 2 standard deviations above? The probability of being in that range is about 95%. So in other words, this is kind of a 95% confidence interval, if you will. I know that if something is normally distributed with mean 20, 95% of the time, a random draw from that distribution is going to be somewhere between 2 standard deviations below and 2 standard deviations above. Or in other words, between 14 and 26. And again, if I go out to 3 standard deviations, I have, so basically from minus 3 sigma to plus 3 sigma, or this 6 sigma range, I'm very, very certain, or highly confident that I'm going to get a draw in that range from 3 standard deviations below to 3 standard deviations above. It's very unusual if something's normally distributed to get a random draw that's outside of that range. So again, if I have something with mean 20, standard deviation 3, normally distributed, I'm over 99% sure that it's going to be between 11 and 29, right? So if the standard deviation were smaller, this would be tighter in, and I would be 99% sure about a smaller interval. But on this particular one, I can say for this normal curve defined by the mean and standard deviation, I'm 99.7% sure that every draw I see or every event I see that's defined by this curve is going to be somewhere between 11 and 29. All right. Let's do another one. Let's say, for example, again, let's talk about a hypothetical investment. Let's say the average return on this investment is 8%, and the standard deviation is 6%. And let's say it's normally distributed. It's not a very good assumption about investments in general, but just for the purpose of example, let's say this one is. So 8% mean, 6% standard deviation. Let's go 6% out one at a time. Let's go 6% out to 14%. That's one standard deviation. 2 standard deviations out gets me a 20% return. 3 standard deviations out gets me a 26% return. Let's go the other way. 1 standard deviation below the mean is a 2% return. 2 standard deviations below the mean is actually a negative 4% return. And 3 standard deviations below the mean is actually a negative 10% return. So this is what my returns would look like for this investment. So if you want to say, give me a range of returns that you're 95% confident this investment will return over the next year, if I want to go to my 95% confidence interval, I've got to go 2 standard deviations below and 2 standard deviations above. Right? This is my 95% interval. So I'm 95% or 95% probability that the return will be somewhere between negative 4% and 20%. So that's a wide range. That's how the standard deviation, that's how you can think about the standard deviation denoting dispersion around the mean. Yes, my average return, my mean return, or my expected return, if you want to think about it that way, that's 8%. But actually, if you want a range that I'm 95% sure returns will be in, well, they'll be anywhere from negative 4% to positive 20%. So you can see how some people might be interested in finding an investment that has the same mean return, but maybe the standard deviation is only 1%. All right. If you do that, then these become 9, 10, 11, and these become 7, 6, 5. All right, so if the standard deviation is 1%, now my 95% interval is 6% to 10%. A much tighter range, right? So I'm not getting this big upside because the volatility is much less, but I have a much more predictable set of returns because the dispersion around that 8% mean is much lower. Okay, so those are some of the basics about the normal curve. We'll talk next about how to set these up in Excel. I do want to give a word of caution here. There are many, many things in life in general that are normal. Machine errors often can be described well by normal distribution. Test scores are typically normal distributed. Travel times are often normally distributed. Market returns, although I gave a market return example here just for something that's easy to understand, market returns in general are not normal. People have learned the hard way by using these oversimplified models that assume normality. In reality, market returns don't look exactly like a normal curve. In fact, there's this concept that you might have heard of called fat tails of the distribution. So a normal curve has very thin tails. In other words, once you get very far out from the mean, these probabilities get extremely small. Remember, the probability is the area under the curve. So if you get way out here far from the mean, that probability is extremely small in a normal curve. Think about it. It's 99.72% of the time you'll be between 3 sigma below and 3 sigma above. Right? But market returns have been shown to have a little bit fatter tails, or in fact, it's sometimes even a lump in the tail, right? So even if you're there's this non-trivial probability of events that are very, very far from the mean return. So even if a mean investment, even if you know the mean of an investment, you can't assume that it follows a normal curve and that there's almost no possibility of a return that's, say, 5 standard deviations below or 6 standard deviations below. With a normal curve, the probability of something 6 standard deviations from the mean is essentially 0. But in market returns, we see those 6 standard deviation events. So that's just a digression into market returns. They're not generally, it's not in general safe to consider them to be normal, but certainly many other things, travel times, machine performance are. Okay, let's talk about using Excel to compute normal probabilities. There are 2 Excel functions that are related to the normal. The first is normDist, and the second is norminv. There are others actually, but these are the 2 that we're going to focus on. These are the English versions. Since this program is in English, I'll be using the English versions of these Excel formulas. If you're using another version of Excel, the translation is fairly straightforward. So what does normDist do? NormDist is you give Excel a particular number and it gives you the probability of an outcome less than that number. All right, so what NormDist takes is First you give it an x, the number that you wanted to look up, then you tell it about the normal distribution. What's the mean of the normal distribution you're talking about? What's the standard deviation? And then you put this last value true. It needs another argument here, so we put true on that. Let's start with norm dist. So let's say, for example, we'll come back to norm inv later. For norm dist, let's say I've got this normal distribution with, say, mean 110, and the standard deviation is 10. So let me draw this really quickly. So we go out 3 standard deviations to the right. This will show most of the curve. And now we go down this way. All right, so the first thing I do is I draw my normal curve. It's mean 110, standard deviation equals 10. Okay. Now I have a question. I want to know what's the probability of a random draw from this normal curve being less than 107. All right, so where's 107? It's right here, right, roughly speaking. So I want to know what's the probability of less than 107. I want to know that area, right? Excel can tell me that area. The way I do that is with norm disk. I say equals norm disk x. The x that I'm interested in is 107. And then I tell it about the normal distribution. This normal distribution has a mean 110, standard deviation 10, and I put in true. That's going to give me this area. Importantly, the norm dist function always gives you the area to the left of x. All right, so it's going to give me this area. It's not going to give me the area under the curve to the right of x. I told it my x was 107. I described my normal distribution. It gave me this area to the left of x. Okay. What about norm inv? The norm inv function in Excel. It needs a cumulative probability, so you give it a probability, and then you tell it about your normal distribution. What's the mean, and what's the standard deviation? So the way you would use this is if you know the probability but you don't know the x. All right? So let's say I've got a normal curve. Let's do a different one here. Let's say mu equals 10, sigma equals 1. So I draw my normal curve, 10, 11, 12, 13, 9, 8, 7. Okay, now I want to know, I'm trying to figure out the point at which I've got a 75% chance of being less than that point. So I don't know exactly where it is, right? I know it's over here. I know that if I choose the point 10, I've got a 50% chance of being less than that point. So I want to slide over here until I find some mystery number that gives me a 75% probability to the left. So I know the probability that I want. I just don't know what this number is. So that's when I use the norm inv in Excel. I would just tell Excel equals norm inv. The probability I want is 0.75. And my normal distribution has mean 10 and standard deviation 1. Then Excel will tell me what point I need to pick on this normal distribution that gives me a probability of 0.75 being less than that. Okay, let's do a couple examples here. And you can do these along in Excel as you watch me do them. Okay, let's say that the mean time to get to class, this is your commute from your home to class, the mean time to get to class is 15 minutes. And the standard deviation is 2 minutes. Okay, so you've been tracking your travel time to class over a number of days. You find that it is well described by normal distribution. On average, it takes you 15 minutes to get to class, but there is some dispersion around that average. The standard deviation is 2 minutes. So first, let me draw this distribution. So here's the travel times. On average, it takes 15 minutes. But if I go out to the right, it could take 17, 19, 21. 21 is 3 standard deviations above your mean travel time. And I could go down to the left. So the first thing I know is that 99.7% of the time, your travel time to school is going to be somewhere between 9 minutes and 21 minutes. That's based on the information you gave me about the normal curve. I want to know what's the probability of getting to class in 16 minutes or less. That's what I want to know. Okay, so here's when it takes me 15 minutes, 17 minutes, 19 minutes. Here's 16. I want to know what's this probability here? What's the probability that my travel time or that your travel time to class is anything less than 16 minutes, right? 9, 10, 11, 12. I just want to know 16 minutes or less. All right, so I can ask this to Excel, right? I can just say equals norm dist, because I have the x, 16, and I want the probability. So equals norm dist. What's the x I want? I want to know about 16. Tell me about my normal. It has a mean of 15, a standard deviation of 2, and I put true. That's going to give me this probability. All right, in fact, I believe it works out to 0.69. So I know the answer is, if this normal curve describes your travel times to class, the probability of you getting to class in 16 minutes or less is about 69%. And I can reality check that from my figure because it definitely should be more than 50%, right? I've shaded this entire half of the normal curve, which I know is 50%, plus a little more. So it makes sense to me that it works out that I got this answer of 0.69. Okay? Let's do one more. Let's use the same travel data, but I'll ask the opposite type question, right? So I still have this travel data of your travel time to class is normally distributed. The mean is 15 minutes. The standard deviation is 2 minutes. So I can draw it, just like last time. Now I want to know how much time do I need to allow for my probability of being late to only be 10%, all right? Okay, so this is what I want. I want the probability of late to be 10%. How much time to allow? That's the question, okay? So I know if I allow 15 minutes, let's say I leave 15 minutes before class, there's a 50% chance that my travel time will be less than 15 minutes and I'll make it on time. There's a 50% chance that my travel time will be greater than 15 minutes and I'll be late, all right? So if I allow 15 minutes, I have a 50-50 chance of making it to class on time. So I want to be out here. Maybe I want to allow more than that, right? Let's say I allow something out here, right? And what I want is, I only want a 10% probability of being late. So what I want is to allow enough travel time that there's only a 10% chance that my actual travel time is longer than that. So if I leave, say, 21 minutes before class, I only want a 10% chance that my actual travel time is more than 21 minutes and therefore I'm late. All right? So I need to use the norm inv. I'm going to give Excel the probability, and I want Excel to tell me this number. What's the number that I only have a 10% chance of exceeding, right? And that's how much time I'm going to allow myself to get to class. So if I go to norm inv, the first thing it wants is a probability. Now I'd be tempted to put 10% in here, but remember, these Excel formulas always deal with left probabilities, right? So it wants to know, the probability that denotes left of the point, right? So if I want to point with 10% to the right of my point, since the total area under this curve is 1, that means I want to point with 90% to the left of it, right? So that's an important thing to understand. If this point has 10% of the area under the curve to the right of it, it has 90% of the area of the curve to the left of it. And Excel always takes left probabilities. So norm inv of 0.9, and then I just tell it about my normal curve again, 15.2. And that will tell me exactly how much time I need to allow such that there's a 90% chance that my actual travel time is less than that, and I get to class on time. And there's only a 10% chance that my actual travel time is greater than that. Okay? I'll post some more examples online, but hopefully this gets you a basic understanding of the normal curve as well as how to implement it to do some simple calculations in Excel. Okay, I think I'll stop. I won't do my last example. I can just post it online.